In this segment, we'll look at create table lines that create constraints instead of declaring new columns. In particular, constraints such as primary keys, unique keys, and foreign keys. A create table statement may include lines that declare constraints on existing columns rather than declaring a new column. And there are several examples of this in bakery3.sql, which we have up here on the slide. For instance, a primary key constraint declares a column or combination of columns to be a primary key. Bakery3 SQL's customer and product table declarations have such primary key constraint lines. And these each declare column ID to be a primary key. Line item, further down, has one declaring the combination of two columns, receipt ID and line num, to be a primary key. At most, one such key may be declared per table. If the primary key comprises just a single column, you can also just add the modifier primary key to that column's type and dispense with a separate primary key constraint. And table receipt offers an example. Now, declaring a column or set of columns to be a primary key has several effects. First, the database will require each row's key column or columns to have unique values, per our earlier discussion of keys. And then second, it will set up an index on those columns. And third, the columns in question will be non-nullable. If you don't explicitly declare them so, MySQL will add the declaration for free. It's nice documentation to add the not null to them anyway, even if it is redundant. Now, earlier lectures alluded briefly to indexes, describing them as tree-like structures that allow for fast searching in a database. Any database table may have one or more associated indexes. Each index is a tree-like data structure on disk, allowing fast searching for rows of the table based on some key. Indexes are separate data from the table itself, but they're directly tied to it. If you're doing the usual labs for this course, you may have done a Java lab that involved join operations on generated tables, lists actually, of objects. Your solution surely used a number of map or similar data structures for speed. An index on disk performs the same function that a hash table or a binary tree map does in memory, allowing order log-in lookup of data. Now, almost all database indexes are actually B trees, a tree data structure tuned for optimal performance in the slow access, block-oriented world of disk. Now, you don't need to know the details of this data structure, but a brief overview will help explain certain aspects of indexes. And we have a picture up here to look at in the diagram. First of all, B trees have very large nodes, each of them the size of a full disk data block. Now, there are many children, therefore, per node, so a B tree is much wider and shallower than, say, an ordinary binary tree. By the time a B tree is 3 levels deep, it can contain over 1 million keys. And as a result, even a very large B tree has only a few levels, and thus requiring very few disk accesses. Now, keys within a B tree index do appear in increasing order. Thus, queries that use an index often return rows in key order, though this is not guaranteed, unless the query includes an order by clause, of course. If an index uses a multi-column key, the columns in the key are prioritized in a manner similar to that of a multi-column order by. The first listed column is the primary sorting key, and the next is a secondary key, and so on. This doesn't matter too much outside the index, but note that it is more efficient if the primary-secondary column order for the index is the same as your most likely primary-secondary choice of order by. For instance, if you will most often use order by last name, first name, then primary key last name first name is better than primary key first name last name. And order by works fastest when it agrees with the index. Now, a DBMS creates indexes automatically for important columns, in particular primary keys. You may also explicitly add indexes on columns you expect will often be searched to speed those searches. Let's leave this diagram and look at the MySQL syntax for that. That syntax is index, followed by an index name, and then a parenthesized list of column names to be indexed. For instance, if we expect frequent searches by product price, then we might add an index to the Bakery 3 product table like this. The name of the index is up to you, and if you don't supply one, MySQL will make one up for the index. It's good style to give your indexes predictable names, though, and we'll discuss index naming conventions a little later. Now, unlike a primary key, an added index doesn't require that the column have unique values per row. Several products, for instance, may have the same price. If there are only a few different values possible for the row, however, for instance, if all products had one of, say, 3 different prices, then the index won't help much with fast searching. In such a case, indexing on the combination of several columns may be more effective. Indexes are essential for database speed, but don't create them lightly. They're space expensive. A B tree, for complex reasons that we won't get into here, wastes about 1/3 of the space that it uses within these blocks. That's a necessary evil for it to run fast. It's perfectly possible for the indexes in a database, thus, to occupy more room than the actual data. Now, while we're looking at the B tree diagram again, the keys in the B tree index do appear in sequential order, but the rows they refer to do not necessarily appear in the same order on disk. Table rows, even ones that are in order in the table, may appear in a different order than the key values, and may even be scattered around the disk. And the arrows here kind of show that. Each key entry in the index shows where on disk its associated row is, as indicated by those arrows. An index on a key K would operate more efficiently if the rows of the table were stored on disk in the same order as the keys, like that. The reason for this is that a search for a continuous range of keys, say from ID 1 to ID 3, is likely to go through rows that are stored together one after another in the same area of disk. So storage of rows in key order like this results in what is called a clustered index, and it's a slightly more efficient index. And this can be arranged for designated keys. But if a table has several keys, they imply different orders of the table rows. Ordering by ID, for instance, is not the same as ordering by, say, last name. So only one index in a table may be accommodated by storing the table rows in the same order as the index keys. Only one index in a table may be a clustered index. Other indexes must instead deal with rows being in a different physical order on disk than they are in the index, and are thus somewhat slower than a clustered index. By default, MySQL makes the primary key a clustered index. Only one key in the table may be designated the primary key, and it's the most important to make efficient, especially if it's used as the target of foreign keys from other tables. So let's move on to a new topic here, which are unique key constraints. A key has 2 practical purposes: speed of lookup and enforcement of uniqueness. Sometimes you're interested principally in the latter. For example, it's not that common to look up a product in Bakery 3 based on its kind and flavor, but at the same time we would rather not have a product that, or have 2 products that have the same kind and flavor values. We'd like them to be unique per product. And in that case, a unique key constraint is the most appropriate, as in the create table product statement here in Bakery 3 SQL. And this declaration has the same pattern as the index declaration earlier. Unique key is followed by an optional key name of your choice, and then a parenthesized list of 1 or more columns. Unique keys do get indexes, but generally not clustered ones, and they also allow null values in their columns. They enforce uniqueness on their key columns, so this particular unique key would prevent 2 products from having the same kind and price. A good database design says that you should declare a unique key constraint for any column or combination of columns that should be unique, except for the primary key columns, which are already covered by the primary key, of course. So, question 1. Add a constraint to Bakery 3 SQL that reflects the rule that a customer should not offer more than one rating for a given product. And the answer here is that this would mean that the combination of customer ID and product ID in the rating should be unique. Thus, we should add unique key constraint to rating here, giving it the name UK Customer ID, Product ID, more on naming in a bit, and then having it on the two columns, Customer ID and Product ID, so that they will never be repeated on two different rows. Now, question 2. Added indexes and unique keys get names, but primary keys don't. So why does that make sense? Why would we need a means of labeling added indexes and unique keys within a table, but not primary keys? When you think about it, the answer is there's only one primary key per table, so it needs no name to distinguish it from other primary keys within the table. There may, however, be many added indexes or unique keys per table, and labeling each makes sense. Now let's move on to foreign key constraints. We've already discussed foreign keys, of course, columns whose value indicates a primary key in another table for join purposes. The create table statement lets you designate columns or sets of columns as foreign keys via constraint statements like those that appear in a number of the tables of Bakery 3 SQL. This example in the receipt table illustrates the pattern. This line adds a foreign key constraint named FK receipt customer ID, which says that customer ID is a foreign key in child table receipt, which refers to the ID field in parent table customer. In a 1 to n foreign key relationship, the table on the n side of the relationship is the child, and the one being pointed to, the 1 in the relationship, is the parent. Now, in the first set of parentheses for the foreign key constraint, just after the foreign key, you list the columns that comprise the foreign key in the child table. After the keyword references, then you list the parent table, the table being referred to, and in parentheses, after that, the column or columns comprising the primary key in the parent table that match the foreign key columns in the child table. And note that you may put multiple columns in both of these parentheses. None of the foreign keys in Bakery 3 are multi-column, but nothing precludes a foreign key having multiple columns if the corresponding primary key in the parent table has multiple columns. But the number of columns in the primary and foreign key must be the same, and each column in the foreign key must have the same type as its corresponding column in the primary key. You don't have to add a foreign key constraint to use foreign keys in joins, but if you add the constraint, then the DBMS will require that any value for the foreign key correspond to an actual row in the parent table. So if you declare customer ID as a foreign key referencing customer column ID, then you won't be allowed to put a value in customer ID that is not also an ID for some row in customer. In other words, there will be no dangling foreign keys. And when we learn how to delete rows from a table, we'll find that a row C in customer cannot even be deleted unless all rows in other tables, child tables, with foreign keys pointing to row C are also deleted, or at least changed to point to a different row of customer. And question 3. Should a foreign key constraint result in an index on that foreign key in the table containing the foreign key? Will the example foreign key constraint we just discussed result in an index on column customer ID for receipt? And you can always look this up, but first try reasoning out whether an index would be needed and when it would be used if it were needed. And the answer is that a foreign key constraint is generally supported by an index on that foreign key in the child table. In a join operation, where we might have a clause where customer ID equals customer.id, for example, we're going to need to look up the receipt rows that have a matching customer ID. And for that matter, if we are deleting a customer, that will require checking for matching receipt rows to know if the delete would result in any dangling foreign keys. Both these operations would be terribly slow if they required going through the entire receipt table, so an index on customer ID is needed. Question 4. Would such an index follow the usual rule of disallowing duplicate keys, or would it permit them? The B-tree data structure, by the way, can permit duplicate keys if you need. Why or why not? Why would this index allow or disallow duplicate keys? Well, the answer is it would have to allow duplicate keys since multiple rows of the child table may refer to the same row in the parent table. In our example, multiple receipts might belong to the same customer and thus have the same customer ID value. Okay, a final brief point here regarding naming of constraints and keys. As we mentioned earlier, it's good style to adopt a consistent naming convention for the constraints or keys that you declare. And the rule in this class is to use names starting with IN, UK, or FK for an index, a unique key, or a foreign key, respectively. Following this prefix are the name or names of the columns in the index, separated by underscore if there are several. Thus, for instance, UK kind underscore flavor for a unique key on columns kind and flavor, or IN price for an added index on price. And then a special rule for foreign key constraints. The table name itself appears before the column names. So FK receipt underscore customer ID. This exception is needed because MySQL requires foreign key names to be unique across the entire database. If two tables have a foreign key on customer ID, then they can't both name it FK customer ID. Now, question 5. Why not just let the database name the keys for us? It will do so if we don't supply names of our own. To answer this, try removing the names from various key declarations in Bakery 3 SQL and then load the resultant SQL file. Then use show_create_table and the table name in the MySQL client to see what MySQL's idea of a readable key name is. Show_create_table produces a create table statement for an existing table, which would create that table in its current form if the statement were run. So by way of an answer here, I'm going to remove the names from these two foreign key constraints in line item. And then I just sourced the Bakery 3 SQL in the MySQL client. And let's see now what we get if we do a show create table line item. What kind of names do we get? Line item ibf1. Yeah, I don't know what that stands for and I'm not sure I want to. So the lesson is don't let MySQL name your constraints. In all the exercises and lectures, we'll specifically name all constraints and indexes following the naming convention just described.